might say these two and show them to students. So if I've got that, that's that function. Students will be familiar with that function. They know what it does. They know how varying A varies how fat or thin this curve is. They know, most of them, that if you vary C, it moves it up and down. Okay? How, and when I say that to most students, they think I'm insulting their intelligence. So how will varying B affect that graph?
Moving horizontally.
Moving horizontally. Anyone else?
Horizontally down to the left or right.
Horizontally and down to the left or right? Well, we can move it. Immediately here, we're hitting on 2 or 3 things fantastically. We're hitting on the dynamic aspect, we're hitting on the visualization, and we're also hitting on the link between the algebra. You see the algebra functions up there on the left, and the graphs in front of me here. I'm getting bored with dragging that now, so I'm just going to let it play itself. Any suggestions from watching that?
Ooh, it's so nice when it touches the graph. You immediately think, what's the link between B and C? What's the link? Touches the axis.
Yeah. So here, right, from observing that moving, what is B doing? Can you describe what's happening?
Sort of arcing over.
Ooh, envelope.
So, something about moving on an arc. Moving on a, what's moving on a parabola?
The vertex.
The vertex or the turning point. So we can easily do that because we can just add the turning point of F, and there it is. And we can now see this turning point moving on that. It would be handy if we put the trace on that, and then we can now see the turning point moving on the parabola. For this particular curve where A is 1 and C is 4, what?
4 minus x squared.
It looks like it's tracing 4 minus x squared. On there. I'll leave you to sort out the maths behind that. The maths behind that is really nice, straightforward, well within the scope of an A-level student who's just started to learn about parabolas. But it's great. It's immediately got us to a deeper relationship, a deeper understanding. When you actually work through and sort out why it's doing that, it immediately leads to a deeper understanding of what's actually going on with quadratics. Second of my 3. I'm going to start with f of x is x squared. I want to point on this now. I'm going to be a bit clever about the way I produce the point, and I'll explain why this is happening in a minute. So let me just So I'm going to have a point that's defined by a slider, and if I just set my slider here, so it goes from 0 to 10 with a step size of 1. What I'm interested in is the point on the curve with the x coordinate is A. So that's A, f of A. Calculating down the input bar down there. That will give me my point on my curve. I can then do my tangent to my curve, and if I move this point around, we can see it moving up and down the curve. And what I'm really interested in here is the triangle that this tangent is making with the x-axis and the negative y-axis. This triangle here, and you can see if I've got its area. 1, 2, 3, back to 1 again. There is its area. A is the x-coordinate of my point. What's the relationship? And down here, poly 1, that's that number there, that 2 is the area of my triangle. That's what Geogebra does. The question is, what's the relationship between A and the area of the triangle? hard to see there. I mentioned though, and this is the reason why I'm doing this example, I mentioned that not only can we link geometry and algebra, we can link numbers. So actually there's a lot of research about multiple representations and the link between the geometry and the algebra. There's the third one that I think is underused, and certainly underused with a lot of students, is the concrete nature of some numerical to add the third bit to those group of representations. So I'm going to put a spreadsheet on. Here's the spreadsheet. Let's just move this across a bit. Moving the slider. So what I really want to do is I can, if I set this down here to naught, I can record that to the spreadsheet, and I can record that to the spreadsheet, and now I can just do this, and there's the table of values. Numerical, graphical, and algebraic. Any suggestion for what that formula is in terms of the A value? And this is where the numeric really comes in. Don't try and get the formula. Tell me anything about those numbers. Anything at all you want to say about those numbers?
You've got some nice powers of 2, 216.
Certainly powers of 2.
8 times half a squared.
Well, what do you notice numerically about the fractions?
Yeah, it's multiply them all by a quarter, you get an integer.
Right, so basically, because we've got quarters here, if I just multiply that by 4,
Can do B2.
I do want to do B2, thank you very much. B2 times 4. The spreadsheet formula is exactly the same as Excel. Everything's just works the same as Excel, you don't need to worry about that. Put that in there. Again, I'd strongly encourage you to crunch through the algebra and see why that's happening. There's a really nice property which I'm not going to prove, but isn't difficult to prove if you don't know it. It's that the tangent to x squared at a point cuts the x-axis at half the x value. Last one then. That really sort of shows the strength of the numeric. We can get back to. Okay, so similar idea with this. I'm still going to be interested in the tangent to x squared at a point. Let's have this point on here. And I'm interested to the tangent at this point. Now this is a really, really useful tip in terms of using Geogebra, and I'll talk about this when we use that to go things. But one of the most powerful things I've found, I just use this technique so much. If I want the x coordinate of that point A to be a variable that I want to do something with, I just type, say I want it to be called lowercase a, I type a equals x, open brackets, capital A. I tend to think of it as a function. In my head I call that a is x of a. And there we go, and I've now got the x coordinate of a as a value a that I can start thinking about. So here's my question. This is C1, C2, depending on the spec. I can do a tangent at x is a. There must be exactly one other tangent to the curve that is perpendicular to that tangent on there. It will be dependent on where A is. Question is, where is it? I'm lacking the whiteboard here, which is a shame, so I'm a bit busy in there, but we'll go with it. So the question is, I can do it very roughly, and this won't work, but we'll just do it to begin with. Here's a perpendicular to my tangent. There's one place I can move this perpendicular to, so it is also a tangent. If I move this point, I'd have to move this.
In old style, it used to be if a parameter was, with your parametric thing. If the parameter is p, then this other point is 1 over minus 1 over p or something, isn't it? It's there's a relationship between the parameters.
Yeah, so basically, using that sort of idea, what do we know about the gradient of this tangent in terms of A?
2x, yeah.
It's 2A. What do we know about the gradient of the perpendicular? It's minus 1 over 2A. Okay? If we know the gradient of a tangent, do we know the x-coordinate at the point that it is tangent to?
Half of it.
It's half of it. So I want a half of negative 1 over 2A. So let's find that now. I don't know what that number is, and my line is called B. I don't really like that. I don't really name my line L because I want B. So I'm going to say B is negative 1 divided by 2A. Let me make sure I get my brackets right here or it's a mess up. Negative 1 divided by 2A. And then I divide all that by 2. So negative 1 over 2 is the gradient, and that must be 2 times the x value. So if I half it, that will give me the x value. So there's the x value of my point. So now all I need to do to plot that point is B, comma, f of B. Don't even need to work out what that is. I can just plot it in and there it is. And fingers crossed, I can do my tangent to my curve at my point, and I should find, let's add on a point of intersection and measure the angle. And there it is. That wherever I move this, they stay perpendicular.
And it stays on that, it stays level, is it, on the y-axis?
So yeah, so here's the first interesting observation, which somebody's already spotted. If I switch a trace on C and move it, the intersection of my perpendicular tangents move along a horizontal line. Those of you who know your parabolas probably recognise that as the directrix. So if you know your parabolas, that's your directrix, your parabola. Where might the focus come in for us? No, because
It's equidistant half, but above rather than below.
yeah. Anything geometrical? Way of getting this point here, which
Halfway
is
between A and B?
yeah,
Or not halfway, the intersection of...
yeah. So there's actually a completely different way of constructing this, which was alternatively, because I know if I knew the focus of this y equals x squared is at 0.25, I need to further pure now, but if I knew the focus was here, then all I would need to do is draw that on here and draw the line through there and find where that intersects the two curves, and that would be the point where the tangent was perpendicular to the original. So, three of my favourite problems, just starting with a basic parabola, starting with a basic quadratic, and the speed at which you can do that and the depth of understanding you can get to is just fantastic because of this way and it handles the geometry, the algebra, and even the numeric. The fact that you can talk about a physical property of the shape, whether it's the x-coordinate, or whether it's the gradient, or whether it's the area, and turn that into a variable and do something with the variable is the real power of what's going on there. And I find now, when I'm doing loads of A-load of stuff with GeoGebra, my thinking is so much more cross-geometry and algebra than it ever used to be, purely through using this. It's great for doing loads of